Okay. Hi, Utkarsh, can you share your screen? Hello.
Yeah, I can.
Yeah.
I'm trying to share. Yeah, I hope I. Uh, so is it visible?
Yeah. Make it full screen, maybe.
Okay, great. So shall I start
So,
now?
yeah. So, first of all, apologies for this first interruption. So, we will introduce you again and then we will start.
Okay, so the next speaker is Dr. Utkarsh Mishra. He's an assistant professor at Department of Physics and University of Delhi. So he did PhD at HRI, and he did postdocs in South Korea, one in South Korea and another in China. Then he was also in University of Southern California, US, and after that he joined in University of Delhi. So he'll be talking about quantum enhanced sensing with many modalities. So you can start. Thank you very much for talking.
Yeah. Okay. So thank you very much for the kind introduction, and thank you very much for inviting me. So I'd like to thank the organizers as well for the kind invitation. So I'm going to talk about quantum enhanced sensing with many body systems. And when I mean by many body systems, I mean that we have let's say, system of ions or spins, which we can address individually, and we can control their interaction between these spins and so on. So these kind of setups can be created, for example, in ion trap. So, what I'm going to talk about are from these papers here. So the first two papers mostly I will touch in this talk, and the others are for references. So here is an outline of my talk. So I will start with a background of quantum sensing, mostly at the level of students. I have prepared this the first part of my talk. Then I will talk about many body quantum sensors, focusing on the critical quantum sensor. So the using, let's say, for example, quantum phase transition as a tool for, as a resource for quantum sensing, as well as Floquet system for as a quantum sensors. And then I will go to the results and give some future prospects in this direction. So quantum sensing typically used to describe one of the following feature. So either one uses certain quantum objects to measure physical quantities like the temperature, pressure, or frequency, and so on. And the second type of quantum sensor refer to the case when we use certain properties of quantum objects, for example, coherence, whether it is wave-like spatial coherence or temporal coherence, to enhance the measurement precision. And third type of quantum sensors belongs to the where one uses entanglement as a resource for quantum enhanced measurement. So I will mostly be talking about type 3 quantum sensors. So when we use a quantum system, for example, atoms or molecule or collection of atoms, collection of ions for a quantum sensor, as a quantum sensor, then what sort of properties this system should satisfy? So to function as a quantum sensor, a quantum system has to have a discrete and resolvable energy levels. And the second condition is that it must be possible to initialize the quantum system into a well-known state. And then it is also feasible that we can read out the output state, because the output state will carry the information about the unknown signal that we want to sense using the sensor. And the third property is that this system should be coherently manipulated. So we should be able to internally manipulate the state of the sensor. And I will give some examples of this manipulation in my talk. And the fourth quality is that the quantum system should interact with the relevant physical quantity that we are measuring it. For example, if you want to measure the magnetic field, so our quantum sensor should be sensitive to the external magnetic field. So there are experimental implementation already for type 1 and type 2, type 3 quantum sensors in different different setups. For example, in neural atoms, in trapped ions, and other kind of solid state spin ensemble. So these are existing quantum sensors which either use the quantum coherence or some discrete energy level property of the quantum system. So a general quantum sensing protocol consists of this kind of Hamiltonian, where you have an internal Hamiltonian of the sensor, then it interacts with a Hamiltonian associated with the signal, and then there is a control Hamiltonian. So this is kind of a most general scenario for any sensing protocol. So usually we assume that the internal Hamiltonian is known, so we know its energy structure and so on. And then the control Hamiltonian need to be chosen in such a way that we can manipulate the sensor in a controlled way. And the goal of quantum sensing experiment is then to infer the signal from the effect it has on the qubit. For example, if we are using qubit as a quantum sensor, so signal will affect the qubit, and then we want to use a control to manipulate the state of the qubit and read out the final state of the sensor to infer the signal. So this is sort of a general sensing protocol. So for example, one of the earlier protocol is based on the Ramsey measurement experiment. So in this experiment, one has an internal Hamiltonian with so it's like a two-level system. One can do it for complicated system as well, but let's consider a simple two-level quantum system with energy levels E0 and E1 with frequency with energy level difference omega naught. And the goal is to see the effect of the signal on omega naught and infer omega naught. So the protocol run as follows. So we first initialize the sensor in an initial state. So in this case, it is a 0 state, and then performs a transformation so that one creates a superposition of 0 and 1. So here one has to apply in experiment some kind of pulse, pi/2 pulse, to create this kind of superposition state. Then we let the sense, so this is become a probe state, and then this probe state interact with the signal. So in this case, it evolves unitarily using this Hamiltonian, and it imprints the omega naught into this state. Now this state again we can if we measure this state, we will not get any information. So for that, we further perform a transformation and rotate the state into this form. And here, if one perform a measurement, one get the probability. So quantum mechanics gives us the probabilities of measurement, and from this probability, we can infer the unknown parameter omega naught. So the probabilities are directly related to the unknown parameter or the signal omega naught. So that is the basic Ramsey measurement experiment. We need to repeat this experiment many times because we want to estimate the probabilities. So we have to repeat this experiment, and the deviation or the uncertainty in the P will translate into the uncertainty into the measured signal omega naught. So in most of the cases, we are going to get a probabilities as a function of the measured signal. In this case, for example, let's say V, and this V is related to omega naught. And you will get some oscillatory behavior, as we have seen here also. And from this oscillatory behavior, there are 2 points that one can understand. The first is that how to infer the signal V naught, the signal V. So one way is to consider a known value of the signal. And for that value, let us fix that the probability is given. So here in this case, this is a bias point. And at this point, the probability is 0.5. And at this point, the signal is known. Now, any other value of the probabilities due to the small change in the signal is denoted by delta P. And because of this delta P, there will be a uncertainty into the delta V, and that is measured by the standard deviation. So this technique is called the slope detection. So the slope is maximum here, means the sensitivity is maximum in this region. So one measures the deviation in the probabilities by the small change in the signal and sort of infer the value of the signal itself. So that is the one point. The second point here is where there is no change in the slope. So this is a linear behavior usually with the delta P and delta V. But when we don't have any change in the delta P, then we have to go to the second order, higher order moments of delta V, and that is called the variance detection. So in that case, you choose some reference point. Let's say P V is equal to 0 is the reference point, and the change in the delta V will be captured by change in the deviation in the probabilities, and the corresponding standard deviation will measure the variance. So these are the standard protocol for measuring any signal using the slope detection and the variance detection experimentally. So this is what people do in experiments. So this is what I have written here, what I have told, that the transition probability P as a function of the signal V is given in that previous plot. So the one way is the slope detection. So you choose a bias point and see how the probability changes from this bias point with a small change in the signal, and that will give us the uncertainty in the probability, and in turn it will be related to the uncertainty in the signal. The second choice is the variance detection, and it is certainly can be shown that it is the second order fluctuation. It captures the second order fluctuation in the signal, change in the signal. And in that case, of course, the slope detection will not work. So when the slope detection does not work, one has to go to higher order moment. So this is the variance detection. So gamma here is the coupling parameter between the qubit and the signal. So going beyond these Ramsey measurement experiment and giving a general perspective, so a general parameter estimation protocol run as follows. So one prepare initial state. So for example, in the Ramsey measurement experiment, we initialize the system in 0. So in general, one can prepare any initial state, whatever experiment allow to prepare. And then encoding is the part, for example, here it was evolution was the part where the parameter is encoded. So here a general parameter theta naught is encoded into the probe state. So this is the probe state. So there is some evolution. So this evolution could be not only unitary, but it could be a general evolution here as well. So it will encode the unknown parameter theta naught into the state. And then of course we have to perform measurement. So the measurement will give us a set of probabilities. And from that probabilities, we have to estimate the unknown parameter theta naught. And we have to repeat this process several times in order to get minimum error in the estimation. And this technique has been used in various physical systems, for example, making the atomic clock or in the magnetometry, or also one uses the squeeze state in the gravitational wave detector interferometer to enhance the precision or to detect the smallest and small signal. So there are various ways one can use this quantum sensing protocol. So a general perspective then leads us to talk about the quantum metrology. So again, we are in initialization, encoding, measurement, and detection scheme. Okay, so suppose we prepare our system. We prepare many copies of our system, and the preparation procedure is independent of each other, but they does not change anything. So the same preparation procedure, same encoding procedure, but one perform independent measurement on each copies of the system that one prepares. So in that case, let's say mu1, mu2, mu1 are the number of measurements that one performs on each copies. And then, of course, we will get the probabilities, as you have seen earlier, for the jth outcome. So if you perform measure, you get jth outcome, and that is the corresponding probability. And this is the conditional probability. So given a theta naught, this is the probability one will get. So a combined probability distribution is given by, because they are independent measurements, so it is given by the product of all these measurement outcome. So for example, if you have a spin half particle, then you have two possibilities, either up or down. And this is a random sequence of measurement of the state that is obtained, let's say, after the encoding. So we know that from our previous Ramsey experiment, that the number of times we will get spin up is given by cos square theta naught by 2. And the number of times we will get spin down is given by sin square theta naught by 2. So this is the joint probability distribution. So we then construct a histogram using this joint probability distribution. And the histogram will have a maximum at certain value of the unknown parameter theta. And that is called the maximum likelihood estimator. So here, if you notice theta here is the estimator. So the estimator is a function. If you give a measurement in outcome as an input to this estimator, it will give you some estimated value of the unknown parameter. So here, the theta ml is the maximum likelihood estimator, and it is sort of have a maximum value of this probability distribution P mu theta will have a maximum value at certain value of theta naught. So the average value of this using this probability distribution is given by sum of all the outcomes, theta mu vector times P mu vector theta naught. And the width of this distribution will give us the uncertainty of the measurement. So this is given by delta theta square and this difference. And here everything is general. There is nothing specific assumption or nothing specific system has been taken. So now it brings us to a famous Cramer-Rao theorem, which tell us that the bounds on the statistical variance of any estimator. So here theta could be optimized over all the estimators. So this capital theta is estimator, but it could be any estimator. So the Cramer-Rao theorem tells us that bound on the statistical variance of any estimator is bounded by the Cramer-Rao bound, where this this uncertainty delta theta CR square is given by the maximum likelihood estimator derivative with respect to the theta at the point where we want to estimate. So let's say theta naught is the point divided by m. M is the number of measurement of the experiment or repetition of the experiment, and f theta naught is the Fisher information, which is given by this formula. So this tells us that the uncertainty in the measurement will never sort of cannot be arbitrarily small. It is always bounded by the inverse of the Fisher information. So if we want to have a minimum uncertainty in the parameter estimation, we have to choose our encoding procedure measurement in such a way that it gives us a maximum Fisher information. So this is the uncertainty given by the inverse of the Fisher information. So if we go beyond the classical route, so far we have assumed that we are measuring up and down as a measurement. So if we go, so far we have only used these conditional probabilities and they are sort of normalized to 1. But if we allow any generalized measurement in the state rho theta, so E is any generalized measurement operator, and it is given by so the probability then will be given by the Bond rule, as we all know. But here we are not specifying that E is a complete set of, E is only the projective measurement. E mu could be any set of generalized measurement. And in that case, the Fisher information will depend upon the type of measurement. And if we optimize this Fisher information over all the choice of measurement, then one gets what is called the quantum Fisher information. The quantum Fisher information is always greater than the Fisher information that we have only using one measurement option. And in that case, if we replace our Cramer-Rao bound, earlier Cramer-Rao bound, by the quantum Fisher information, then this is the earlier Cramer-Rao bound, and this is the quantum Cramer-Rao bound. So it tells us that the uncertainty will further decrease as we choose further optimization. And this optimization is done over all the choices of the measurement operators. So this is the quantum version of this Cramer-Rao bound was done by Bronstein and Caves back in 1994, and also the Hellstrom in other version of this bound has been discussed by Hellstrom as well. So we are going to use this benchmark formula. That what system we choose to get a higher Fisher information, and this will lead us to a lower uncertainty. And this is what our main purpose is in the sensing protocols. So if one asks that what is the ultimate limit of precision set by fundamental laws of quantum mechanics, then those ultimate limit of precision is given by the Cramer-Rao bound. So it means that the uncertainty in the measurement cannot be lower bound, cannot get lower than the inverse of the quantum Fisher information. So now, if we have an independent number of qubits, and we pass each qubit through a encoding procedure, and then we perform measurement on the individual qubit, then the maximum Fisher information. So if there are n number of such qubits, then the maximum Fisher information can scale linearly with this number of input probes. So in that case, the uncertainty can go as 1 over m times n, where m again is the number of repetition of the experiment. And this limit is called the standard limit of measurement precision. Now, on the other hand, if we use the entanglement, then what is the improvement that we can get in the measurement of any parameter? So let us consider that we, instead of this independent probe, so again we consider that we have some independent probe which are initialized into a 0 state, and then we somehow create entanglement between them. Now this task is experimentally not very easy. I have draw this box and mentioned that in the apply entangling operator, you get entanglement. But for experimental colleagues, this is something very challenging, and they will not, I think, agree with this, that it is sort of just drawing this will make anything. But just for understanding, let's say that we have n qubit and we create an entangled state out of these n qubits. And this is a well-known entangled state called the GHZ state. And now we do the evolution process and imprint this unknown parameter theta into this GHZ state. Now we'll see that in the output, we have a signal which is given by theta is amplified n times here. So the use of entanglement is that it will amplify the signal. And now we have to perform measurement. So this is very similar to what we have learned in the Ramsey interferometer or Ramsey measurement scheme. So again, applying some disentangling operator, we just separate out one qubit and leave everything else into the 0-0 state, and then we perform measurement. This measurement will again give us the probabilities, and if we again do the same analysis, what we will obtain here, that this delta theta squared will no longer scale as m times n, rather than there will be an improvement of 1 over n factor. So in this case, the uncertainty in the estimation of theta will even be lower when we use entanglement as compared to the case when we don't use entanglement. So that is the quantum advantage that everybody is sort of trying to achieve, that using entanglement, the precision that they want. So actually stand for the Heisenberg scaling. So everyone sort of trying to achieve the Heisenberg scaling of the precision in sensing protocol. So, for example, this back in 1994, David Wineland and the collaborators have demonstrated the Heisenberg scaling. So it means that they have created entanglement in experiment, and by performing the measurement of certain corrective operators, they have shown some improvement in the measurement. So here is that paper, which shows that they have achieved the Heisenberg limited spectroscopy with multi-party entangled state, and this paper is back in 2004. So they have shown that there is a spectroscopic sensitivity attained around 2 times as high using the entanglement as of 3 non-entangled particles. So entanglement certainly can be created and experimentally used for the quantum metrology or quantum sensing. Now, but the only problem here is that this kind of entanglement, the jet kind of yes.
So you have
Yes,
10
yes.
minutes more. You have to finish within 10 minutes.
10 minutes.
Yes.
Oh, sure.
Okay.
Okay. So now the problem with the GHZ state is that it is very fragile against the decoherence. So even if you trace out 1 qubits, you don't have an entanglement. So and also they are not interacting with each other. So this entanglement is sort of created in such a way that these qubits don't interact with each other. Now, but in real life, in real physical system, we do have interaction, right? Now, in this paper, for example, they have performed quantum metrology with a strongly interacting spin system, where they have shown that the sensitivity is decreasing linearly as a 1 over n. So you can relate rho times, so T2 is the coherence time, rho is the density of the particle. And those particles are the NMR, nuclear magnetic spin ensemble here. So what they have shown that as you increase the density of the particle in a confined region, they will naturally start interacting, and then in that case, you will not be able to achieve even the classical standard limit. And what they have performed certain decoupling operation to achieve the higher precision. Now, what we consider in our work, that instead of performing this decoupling operation, cannot we use interaction in some way to enhance the precision of quantum metrology? So for that, we consider a many-body system. So this is a many-body system, which is XY Hamiltonian. So this is the internal Hamiltonian you can think of, and this is a signal Hamiltonian. So we want to estimate the unknown magnetic field H0 here. Now this system undergoes a phase transition. So this is the phase diagram of this model. So around certain critical value, there is before that there is a order phase, and beyond that critical value there is a disorder phase. So MX is the order parameter. So so criticality-based sensing means that we use the quantum criticality as a resource for performing the quantum metrological protocol. So here F is the fidelity between 2 nearby quantum states, and DH is very small, so we can expand this formula to the second order or higher order and just take the second order term. So we know we can observe that this chi F is nothing but the sensitivity. It measures the sensitivity of this function with respect to the change in the parameter that we want to estimate, in this case the magnetic field. And around the critical point, the scaling of this function is similar to n square times d nu. So d is the spatial dimension, nu is the critical exponent. So if this denominator is 1, then chi f scales as n square on the critical point, and away from the critical point, the chi f scales linearly with the system size. And there is a linear relation between the chi f and the Fisher information. So it has been shown that the around the critical point, the Fisher information scales quadratically with the number of qubits that are interacting with the system, and away from the critical points, it scales linearly with the system size. So criticality certainly can be used as a resource for quantum enhanced sensing. one can also physically understand this phenomena, because around the critical point, the state is very sensitive to any small perturbation. So even if we change even there is a small signal is very tiny, and it is sort of if it is around the critical point, and if it fluctuates around that point, there is a huge change in the state that we can use for estimating the parameter. So, there are recent experiment on critical quantum metrology, but this experiment has been done only for 2 qubits and first order phase transition. So for second order phase transition, recently, I think there have been some experiment also as well, but they are sort of after our work for sure. Okay, so now, in most of the cases, if we have let's say n spins, our goal is to perform measurement on all the spins. Now we thought that can we achieve Heisenberg kind of scaling even if we do not measure everything, we just measure part of the system. Let's say, so suppose we have a XY Hamiltonian with n number of spins, and we just measure L number of spins, and we see how does these spins get the information, how much information do they get about the unknown parameter. So this we call at a partial accessibility. So we only are able to access the system partially and not fully. So the partial accessibility can be translated into mathematical form where we trace out everything else. So suppose we have n particles, we trace out everything else except L qubits. So we have a density matrix of L qubits. So now again, we consider this XY Hamiltonian. H0 is again the field that we want to estimate. And so this Hamiltonian can be diagonalized, and its states can be accessed through the fermionic correlation function. So the reduced state can be characterized by the bipartite fermionic correlation functions. And the Fisher information so the Fisher information can be related with this gamma matrix, where gamma matrix is made up with this correlation matrices. So Carlo and others have derived this formula. So now here is the plot of the ground state quantum Fisher information as a function of the Hamiltonian parameter gamma H0 for L is equal to 2, L is equal to 4. So see, the total system size is 6,000, but we are only working with the 2 qubit or 4 qubit system. And we can clearly see that around the critical point, the Fisher information is quite high as compared to the other region of the parameter. So what we can infer from these plots that the subsystem quantum Fisher information can sense the critical point in a similar fashion, the Fisher information of the total system. And then we also perform a scaling of this quantum Fisher information in the ground state as a function of the number of qubits that we can access. So again, we perform measurement only on 100 qubits and the total system size is 6,000. And we can clearly see that around the critical point, so we perform a curve fitting of our numerical data for different values of gamma. And what we found that so usually if we take a full system, then this scaling, as we have seen, should go as n squared. But here we see that for different values of gamma, this scaling is less than 2. So we wanted to improve this scaling exponent. We wanted to improve this scaling exponent here. And for that, we devised a method. So instead of working in the ground state, we bring the system away from the ground state. So we consider a time evolution of the system by applying a time-dependent magnetic field. So this you can think of as a control parameter. And so here we have to control omega, T, and H1. These are the control parameter. And we want to estimate H0. So these are the mathematical formulation, which is already well known in the literature to find out the time evolution state. And if you go to the momentum space, you can sort of write down the full state in terms of the momentum variable and so on. The important part is that if you keep driving the system for a large number of driving cycles, you will achieve some kind of steady state where the time-dependent terms in the thermodynamic limit will vanishes due to this Riemann-Lebesgue lemma. So this has been also studied well and earlier. Now, why I'm talking about the observable? Because eventually we will calculate this correlation function, time-dependent correlation function, and their large time value. And this will give us the steady state Fisher information. So here we plot the steady state Fisher information as a function of H naught for different number of partial accessible qubits. So L is equal to 1, 2, and 4. The total system size again is 6,000 for two different frequencies, omega 1 and omega 2. Now what we found that in the ground state, there was only two peaks at H naught is equal to 1 and -1. But when we drive the system and go to the steady state, we have multiple peaks. And even if we go to the lower omega, the number of peaks are even stronger. So not only we can estimate the value at H naught is equal to 1 and -1, but we can also estimate other values of the field by driving the system. Now, the reason for this multiple peaks is that we have the physics now is governed by the Floquet spectrum rather than the ground state spectrum. So there is a this what is called the Floquet resonance occurs at different values of H naught for different frequency, and where there is a Floquet resonance occurred, we have a peak in the quantum Fisher information. So this is very similar to what we had in the ground state. In the ground state, the energy gap is minimum around the critical point, so we have a peak in the Fisher information. And similarly here, we have Floquet band closing at certain values of H naught, and we have a peak in the Fisher information. Now, furthermore, we again perform the scaling of the steady state Fisher information as a function of L for different frequencies. And we fitted, so this there are triangles are data, and the line is a fitted curve. And we found this exponent by curve fitting that goes around the Heisenberg scaling and even goes beyond the Heisenberg scaling. So the conclusion here is that by driving the system with a suitable frequency, we can achieve the Heisenberg scaling, even with the reduced, even with the partial accessibility, and we don't need to perform measurement of all these qubits. So we also realize this system in a sort of a smaller setup. So this is the system that people can create in, let's say, in iron trap, where the spins are not only interacting to nearest neighbor, but there is a sort of long-range interaction between them, a variable interaction between them, and we perform certain observable here. So this is the figure A and figure B. So figure A is the plot for the transfer field Ising chain with a short-range interaction, and figure B is the transfer field Ising chain with a long-range interaction. And if you see the blue curve here, which is basically the quantum Fisher information, they are excellent matching between these two. So even if you sort of work on a system which is not transfer field Ising type, still we can sort of see that we can simulate the quantum Fisher information. Okay, so in summary, we have sort of proposed that we can have a quantum sensor made up with the Floquet driving, which is akin to the critical quantum sensing. And we also say that by only accessing partial degrees of freedom, not the full system, we can achieve the Heisenberg scaling. And we also demonstrated that if we have a NIST kind of simulator, which can simulate the many-body system, then we can also implement our protocol there. Now, the future work that are interesting are that suppose, so if we talk about magnetic field, the magnetic field has a 3 direction, X, Y, and Z. So can we have a protocol where we can estimate, all these 3 parameters together? So there are certainly work in this direction, but there's a lot of things which one can do in this direction. Also, we haven't considered the effect of noise, whether noise will keep the Heisenberg scaling or we will not get Heisenberg scaling and so on with the noise. So these are still very much open question. So now I will just bring this very nice review to the audience written by Peter Zoller and June. So they can have a look at the use of quantum sensing for not only for, let's say, magnetic field detection or electric field detection, but also to sort of discover some new thing in the fundamental physics. Okay, so with this, I'd like to thank the people who are involved in this work. So Abul was the group leader, and Victor was my collaborator as when I was a postdoc in China. And I also carried out this work sort of when I was in USC, and I have a long collaboration with people at HRI. So with this, thank you very much for your kind attention.
Okay, thank you, Utkarsh, for this nice talk. So, is there any question? I know you are all very hungry, but still. Question?
Hello, sir.
Hello. Yeah, you are audible, yes.
Okay, sir, you told about that when we apply the entanglement, then it enhances the output of the component. So
Yes.
my question is, so if we are taking any real system experimentally, so like spinning liquid or other things, so their entanglement, the making the singlet is continuously changing the position. It is not the fixed spinning what it's called singlet. Its singlet is always changing the position. So it is really applicable to the experimental, how to control this qubit for experimental purpose.
Oh, sorry, I didn't hear your answer, but as long as you have an entanglement, so singlet is like if you have like two spins, then you of course have a singlet. Then certainly, I mean, as long as you have entanglement, there will be improvement. But what people want to create entanglement between large number of particles, like jet kind of state, noon kind of state. And they're certainly not very stable states. So, for example, here in our talk, we haven't used explicitly an entanglement. So the only thing that we have is a quantum critical point as a resource.
That's
so entanglement.
Yeah, it's not a stable state, but it is always changing the singlet position. No? It's not only the two spins singlet is making, it's always changing. So how we apply it in a real system, in experimental? That's
how we apply it?
In real experimental things. It is theoretically modeling is okay, but it's possible to apply it.
Yeah, so I mean, people have done this in 2004. I mean, this experiment.
Why you are saying the singlet is changing?
Changing it we are taking the spin liquid state. Then not only singlet making on the singlets with sputterings, because they are making with another. So that gives us this we can also sustain. Like suppose you have a lab case. Experimentally, you are taking any materials. Yeah, in experimental. So if not singlet is not only making the nearest spin not it's making the sputterings with another sort. So when you apply it in the experimentally real apply that told that anything also is for adjacent and you want to create a simple different type. So you are talking about some particular example. It's not that all the systems are like that. And what is saying here is like a GT state. For example, here it's like a all 0 0 or say all down down. It's not goes with all up or all 1.
Let's talk spin liquid. So which is superposition of many transparent.
That kind of entanglement we can apply or not? That's my
question. So I mean, GHZ state is not one kind of entanglement. You can apply noon state kind of entanglement as well. Squeezing, for example, is another quantum state which you can apply. So for the kind of state that you are talking about, I couldn't hear properly the question, but certainly one can devise a protocol where one can see how much advantage that state will give. I don't have a definite answer to that question.
All right, any more question? So if not, I have actually two. So one is that, are you also thinking about some small scale implementation of this theoretical scheme in experimental scenario? Is there any plan?
Experimental implementation?
Yeah. So the protocol that you have talked about so far.
So
how much is feasible to translate in next? Sometimes we cannot measure quantum Fisher information
Yeah,
theory?
okay. So I think there I have seen some papers where they can apply this. They can certainly so they can certainly measure the partial system. That much is possible. They can certainly measure a few number of qubits and they can perform the sensing protocol. So that much people can do in experiment. Let's say in cold terms, for example, they can perform the experiment where they can access the partial accessibility.
All right.
For Floquet, I have to think about it.
Okay, and another thing is that when you, let's say, you have shown in some cases you got enhancement, right? So is there
Yeah.
any intuition that what should be the model and we should start with, if I do all these things, so it's not likely that we're going to get this enhancement in all the cases, right? So is
Yeah,
there
so certainly there's no, right. Yeah, so for example, there's a derivation for a critical system, which is very general. I mean, this part of derivation is very general. So if you have so this is like finite system scaling derivation. You can sort of believe that the second order phase transition will give you a enhancement, right? So that is sort of, but in a very general scenario, let's say for example, first order phase transition. Now, in the first order phase transition, the gap closes exponentially with the system size. So certainly that protocol is not directly experimentally implementable, but these people have cleverly implemented the first order phase transition and sensing in the very first time. So this is not something sort of like just they have directly implemented. They have really cleverly sort of used adiabatic protocol and device to create use the criticality to sort of achieve the Heisenberg scaling.
all right?
So yeah, so in general, picture is sort of not very. There's no such proof, I would say.
All right.
Hello, Utkarsh. Abhijit here.
Hi.
So
Yeah,
you
hi.
showed that this Heisenberg scaling is 2, right? Yes.
2 years, yes.
So you are getting the scaling 2.15. So this is not the ultimate. So there is also other papers on in the context of laser. And why can I say
Yeah.
that what is the ultimate bound? Like can you predict with this kind of model you can the ultimate scaling is n equal to 3 or something like that?
Yeah, so that is a very good question that, I mean, how much it can keep going, right? I mean, beyond 2, right?
So is there any ultimate bound that you can
Yeah, so these numbers certainly, yeah, okay. So now, one thing that we know that this Kramerov bound is something that is even for the case of n square, it is optimized over everything, optimized over initial state, optimized over encoding, optimized over estimators. But in the practical scenario, we may not be even achieve, let's say, Heisenberg scaling too.
Yeah.
So the more fundamental thing is that what kind of operators we can measure. For example, here, what is the operator that we can measure and how much scaling we can achieve? So that is the more important question. The ultimately been sort of so again, I mean, in that case, Sudipto question is very relevant because can we achieve this experimentally? For example, this ground state criticality, people have certainly achieved. They have performed experiment. They have said that it can go L squared, but they have not achieved, let's say, beyond 2. So similarly, I would say that here, if they achieve more than 2, that would be sort of then very interesting. But for all practical purpose, how close we can go beyond, let's say, linear scaling, that is the more interesting question. What kind of operator we should measure, what kind of operator our experiment will give us, that sort of is more interesting. But yeah, so I mean, I don't know how much far it can go because for example, in other paper that we did, even we go beyond 2 actually, I mean, beyond 3 as well. So for example, with Devrajda, we had paper where we have gone beyond 3. So certainly that is an interesting question to address from the theoretical point of view.
Okay, thank you. Thank you again for the nice talk.
Yeah, let's.
Yeah. So thank you very much, everyone.
See you again.
See you.
Okay. So all right. So with this, we